Okay, let's continue with the lecture of optimization concept and applications. Now we're going to talk about general settings, the standard form of optimization problem. Here's a quick overview, a very quick overview of what is the definition of optimization problem. In a loose sense, an optimization is a mathematical problem where you want to find a variable. Sometimes it's called a parameter. Let's call it x. All right. You want to choose some quantity, some variable x that makes some objective function to reach an extremum. An extremum could be a minimum or a maximum. Okay. When we talk about optimization, it contains 3 elements. The very first one is the choice that you make. What are those things? All right. That is called optimization variable. Sometimes it's called decision variable as well. Okay. This is the quantity you want to choose to achieve the optimization goal. Okay. With that example, I wanna do the pricing. Okay. I have a product, right? I want to determine what price would be. My price is optimization variable. Second of all, the second element is objective function. Okay. When you want to decide about that x, what would you like it to be what is your goal? Okay. How can you describe your goal as a mathematical expression? I want to decide my price so that my profit is maximized. The profit is objective function. Last one, a lot of times we cannot choose x freely. We don't have that, that infinite choices. When we have restrictions on x, conditions on x, that is called a constraint. You can have more than one constraint. Now, this is an example. And I would like, one of the basic things is that once you are given with these 3 elements for a simple problem, can you sketch it graphically? Okay, so this is a function of one variable. This is the blue one, is your objective function. And then you see that there are three extremum. You have the maximum one, the 2 maximum ones, and you have 1 minimum. All right. This interval is an example of constraint on your x. I only want to find x within this interval that minimize my function. If you take a look at this graph, if the aim is, minimize fx subject to x belong to that interval, the minimum would be, so I need to draw, right? I need to draw the interval. The minimum would be here, right? The minimum would be here. So I say, my x is supposed to be here so that my function reach the minimum, right? On the other hand, if I change my problem, can you maximize my f where my x belong to that interval? So it's that one, okay? So all the 3 elements will be used to find the solution. Now let's move to a more general case. Now you have a function in R2. Okay, there are 2 examples. These are when you see the blue ones are level sets or contour. Okay, or contour. In this example, let's assume that the outward of the contour corresponding to greater value of f, gradient of f, like in that direction. Like think about you in R2. This is your R2 plane, right? And like the contour is where you look at here, and the pink one is the constraint region. You only want to find x within this region, okay, where you want to minimize the function. Is it hard to look? So basically, the constraint is something you have to satisfy, right? You cannot pick x around here. No, that's not possible, right? Then the contour is how to describe your objective, right? It can be as large as this, right? Or it can be as small as this. Optimization function, optimization problem, roughly you want to minimize the objective where you still satisfy the constraint, which means you want to minimize, right? You want to minimize the objective. The contour in this example, the greater the contour, the greater value in f. So you prefer the contour to be small, right? So, but the thing is, you want to stay on the constraint as well, which means, I'm gonna, should I pick the purple one? Because the purple one, it doesn't show. The purple point, because it perfectly satisfies that it's lie in a constraint, right? And this is my x1. So suppose this is the first choice, right? And I can read that, oh, this is the function value. But the thing is, that choice, is it optimal yet? No, because I can say, no, because I mean, the smaller the level set, the smaller the function values. My aim is to minimize the objective, right? So why don't I use this contour? Why don't I pick this level set? I knew immediately that the orange level set corresponding to smaller value. I'm gonna pick my x2, right? Maybe another one say, no, I'm gonna pick the purple one because the purple one give me a smaller objective value. Can you do that? No, I'm gonna pick x3. Why don't I use x3? Some may say, oh, why don't I use x4? Because the point x3 and x4 do not lie on the constraint. So you violate that conditions that are supposed to be required. Okay? In short, graphically, if you're given an objective function, if you're given the constraint set, if you draw it on the R2 plane, an optimal point is where the level set, you find the level set corresponding to the smallest value as you can find, while the level set still touch the constraint set. Got it? As long as you pick different x on the constraint, that x corresponding to different contours, right? So you pick the contour that is the smallest value. Maybe for LP guys, if you love linear. If your function is linear, just like I have this expression, maybe 1, 2 transpose x, right? The level set of linear function is hyperplane. But when you have two variables, it is what? Linear graph in R2, right? Right? Is x1 plus 2x2 equal to alpha? If I draw, okay, this is one level, right? One level of function value. This is alpha 1, alpha 2, alpha 3, right? The level set corresponding to linear function associated with different function values. Which one is the biggest value of alpha? Rachan. Yep, Alpha 1 is the biggest, alpha 3 is the smallest, right? Now I say my linear function is the objective function. I want to minimize the linear function. But as we see before, the linear function alone is unbounded below, right? Obviously. So minimizing the linear function alone does not make sense. That's why we have the constraint. Suppose the constraint look like this, pentagon. I mean, mathematically, we're gonna see later, this is called polyhedron. Polyhedron is a set of bunch of hyperplanes, like intersection of bunch of hyperplanes, okay? Now, what do we do with this? An optimization is that, can you find X that lies in the pentagon where it still minimize my objective function, which is linear in this example? Should I pick this one? No, obviously not, because it's not in the constraint, right? Now my x1 is this. And I'm going to give you a bunch of x1, x2, x3, x5, x6, x7. For each choice of x, right? For each choice of it, bunch of these x are fine. They are in the constraint, but you don't know yet which one is optimal. So you're gonna draw a level set that pass those x and see which one give you the smallest function values. X3, dude. What do we see again? Alpha 1, is it like the biggest one, right? So basically all these level set, you want level set to be up above or to be below. You want to minimize it. You want it to be, as far below as you can, right? But still, that level set still need to be in touch with the constraint. Right? Which one do you prefer? Yeah. So you move downward until it still give you an intersect point with the constraint set. So in this case, x7 is optimal. Now I'm going to zoom up again. But then why not x6? Why not x6? Because for x6, that's going to be what? This level set, right? That still give you a higher value. Okay, that is a very, this is how you sketch the concept of optimization, especially in LP. All right, when you have a very simple LP, if you sketch this, not a lot of times, sometimes you can get the solution right away. No need to solve the computer. Okay, no. Example optimizations can be found a lot in applications. For example, you have many resources, right? You have many resources. You have many. You want to invest on many many unit, right? And then, but you have when you want to invest something, you want to maximize the profit. Okay, so the profit is objective. This is decision variable. I want to invest 10% on this fund, right? On the first fund, I want to invest 20% on the second fund, but still I have the budget sum. All right, I have a total budget of 2 million. Okay, decision variable, objective function, and then constraint. All right, all the red fonts are the constraint. Okay, now I'm going to jump to the fourth bullet. When you develop a model, whether in machine learning and everything, okay, when you want to find a model certainly contains a parameter. Okay, think about coefficients in linear regression model. Think about weight and bias terms in neural network. All right, that's the decision variable, optimization variable. You want your model to give the least error, and that is the error between y and y hat. Y hat is from your model, so it certainly depends on your model parameter. Okay, and again, you need to come up with a way to measure the error, and that's why error is a vector, right? You translate it, like come up with the loss function. That's how they talk in the field. What is your loss function? It's the same concept as objective function in optimization. Okay, then not done yet. Your parameter, a lot of times, again, you cannot choose it freely. You have constraints. An example of constraint is that if you work with a dynamical model, okay, sometimes you want the model to be stable because it's going to explain a stable system. Just like the gain in the first order transfer function, right? If your plan has a positive DC gain, your K is supposed to be non-negative. Okay, so that is the constraint. Okay. Now I would like to spend maybe 2 minutes, 5 minutes for explaining the problem setting. This is how we explain the mathematical optimization problem in standard form. F naught is called objective function. Okay, your X is in Rn, typically in Rn optimization variable. For the constraint, we have 2 types. The first type is called equality constraint functions. Equality constraints function. You have P of them. You have P constraints. Okay, so like for example, x1 plus x2 equals 3. Sine of x1 plus x2 square equals 6. All right. This H can be linear or nonlinear. Equality constraint. Equality constraint. Question? You have question? Fi is called inequality constraints function, where everything is expressed in inequality form. For example, e to the x1 plus 2x2 less than 5 between 3. Okay? In this form, you have 2 inequality constraints, even though you like express it in one line, right? Okay. Constraint set, like I typically use the letter C. The constraint set is a set of X where it satisfies all types of constraints, both equality and inequality. Okay. Next, the domain of the problem. The domain of the problem is the intersection of all the intersection of the domain of constraint functions and objective. The domain of the function, can you review? If my Fi is the square root of X, what is the domain? Yeah, right. My X has to be non-negative, right? That is a domain. A lot of times, your function has a domain and is not expressed explicitly as a constraint. Cross entropy function, X log X. Suppose you want to minimize this, right? Log X again, X. I mean, we're not talking about finding complex value, right? Like our X is a real vector. So your X has to be what? Again, in the positive, right? I use plus for non-negative. I use plus for positive. Okay, that is domain. Optimal value. Optimal value of a problem. Okay, of an maybe go back again. An optimization problem is stated as a problem, like the whole thing that has 3 elements, as I said before. The definition, the description of What is my variable? What is my objective function? What are my constraints? The one problem states the three elements completely. A mathematical optimization problem is not an equation. Got it? Is not equation, is not an inequality. You don't express this as, oh, equation 1, this is equation 3. All right? The whole thing itself is a problem. Okay. Now, an optimal value of an optimization problem is what? Okay, this is a set. All right. You're going to find an infimum of your objective function where infimum over x, all right, where your x satisfy all the constraints. Okay. When your x belong to the constraint set and is perfectly in the domain of your objective function, we say your x is feasible. Feasible, right? Okay. If the optimal value of your function is infinity, we call the problem is infeasible. Actually, there's no infimum, right? When your problem is unbounded below, we assign the optimal value to be minus infinity. And this case is going to be less interesting, all right? From application point of view, you don't want to propose or talk about a problem that is unbounded below. It's useless, right? Also, you don't want to solve a problem that is infeasible, because you cannot even find x that satisfy the constraint. That it doesn't make sense to even optimize it, right? Then a feasible x is called optimal. Optimal when that choice of x gives you the function value equals to p star. And that x is called optimal with the note that there can be many optimal points. An optimal point doesn't have to be unique. Okay. Maybe real quick. If I say, oh, this is a constraint, right? This is a constraint. My level set again is linear. My optimal point would be so my gradient f is in that way, right? So I prefer the level set that is below, right? So that is the last level set that I should pick, right? Right? But there are many x here that gives me the optimal value. So the optimal x can be many, So I give you a bunch of words, right? Okay, we say x is locally optimal. Locally optimal, it means that when I compare x to any points in the neighborhood, this is x, right? This inequality suggests that any vector z, right, that is not too far away from x when we measure by the 2 norm, and the radius is epsilon. Okay, that is what? That is the region of all points z that satisfy this inequality. It basically say if I try to minimize, right? If I try to minimize that function where my z satisfy the constraint, and my z is very close to x, that choice is the best solution in the neighborhood. Maybe go to one direction. You would understand it better. Okay. Like this. Okay. There's a one x1 star and there's a x2 star. All right. Okay. Where is P star of this function, of this problem? Huh? P star, optimal value. P1 or P2? P2, obviously P2 is the optimal value if I minimize it, all right? We say X1 star is locally optimal, okay? Because if I compare to my neighborhood, all right? If I compare to my neighborhood, f of x, f naught of x1 star is still smaller than the function values evaluated at any point in the neighborhood. Okay. We can come back to this. We have more example. Now we're gonna end the lecture very soon. This is gonna be part of exercise today. Bullet 1, with the concept, with that given terminology, let's review if we understand all of this together. The first function, okay, this is a description where my f naught is objective function, right? Okay, I want to minimize 1 over x without a constraint. How does it look like? 1 over x. Like this, right? Okay. Maybe I sorry, maybe my constraint is in R plus. My constraint is in R plus. Okay. P star is 0 because the infimum of this function is 0. But an optimal point is a point where what? Where it satisfies all the constraints and the corresponding function value is equal to optimal value. That optimal value must be attained at that x, so that you're going to call x optimal point. In the very first example, optimal point is 0. The infimum of the objective is 0, but I mean that x, which is infinity, right? In order to attain 0, can you attain that? No, because x has to be like very, very big. No optimal point, technically, right? The second one, very quick. The second one, minus log x, minus log x. How does it look like? Minus log x, like this. Okay, it has a domain. X has to be in R plus, right? Again, P star is minus infinity, unbounded below. Okay. X, next one, x log x. X log x. Again, the domain is in R plus. Now maybe you don't know how to plot the graph because you haven't seen it before, right? Oh. Maybe we can use the technique from the calculus. We find the gradient first, right? We find the gradient, and that is x log x, log x. Log x first plus 1, all right? What do we do with the derivative? Set it to 0 from the calculus, right? 0 derivative. So x is e to the minus 1, right? Okay, that is 1 over e, but not done yet. Not done yet. This is the point where the gradient is 0. Is it minimum or maximum? You go for the second derivative, which is 1 over x, right? Okay. So if you plug this in, right, 1 over x, of course, is positive. Also, that x is minimum or maximum? Minimum. Okay. Of course, if you plot, it's gonna look like oh, there's a minimum here. Okay. For the fourth example, I hope you do it. That function, the fourth function, does it look very familiar to you? X log x plus 1 minus x times log 1 minus x. What is that thing? Does it ring any bell? Huh? What is that? Oh, x, x log x, 1 minus x. Or think about Bernoulli distribution, right? Bernoulli distribution with the probability of success as x. So the complement is going to be 1 over x. And for those who do binary classification, right? Nacha, Yogon, that is the cross, but with the negative thing, that is a cross entropy function. Okay, in terms of information theory, what do we want to do about the entropy function? Entropy function is like the sum of what pi times log pi with the negative thing, and what I mean in the field of information theory, what do we want to do with the entropy is we want to maximize it. So that's why I flip the sign as the without a negative. It turns out, can you do with the same trick? All right, just the basic calculus. It turns out that x equals to 1/2. It's like Bernoulli distribution with equal probability. That is optimal. Okay, for the rest of them, I hope it's not hard. Maybe I sketch one of them, right? The last one, and we end the lecture. Number seven. I want to minimize this function. How does it look like, this function? Quadratic, right? Quadratic. No? The orange function is the objective. It is actually a circle. Okay, center at 2, 2. All right? But you don't know yet how big it's going to be, right? But you prefer the level set to be big or small? Big or small? This is the level set corresponding to this objective, right? Is it hard? Huh? It's a circle, right? In R2, center at 2, 2. Suppose it's here. But you don't know the radius yet because the radius is something you want to minimize, right? Okay. We have the constraint x1 plus x2 is 2. That's the constraint. How does it look like? The constraint set x1 plus x2 is 2. That's a straight line. Pass here, right? Right? Is it here? Is it like on the whole line, the whole green line, or is it below? Look at the constraint. Is exactly on the green line because this equality constraint. Okay, this is equality constraint. So your constraint set is the whole green line. Do not try to be imaginative that, oh, it's a half space below or up, you know. Okay, what do we do with this? What do we do with this graphically? Again, I want to minimize the cost objective where I stay in the constraint. So I'm focusing on the constraint, right? I want to find all the point, I mean, not all the point, any point on the green line where it corresponds to the smallest value in my function. Should I pick the biggest contour right now? No, right? Are you sure? Why can't I pick this big contour? This is my X. This is my X on the green one. See? My X is on the green line, perfectly on the constraint. That is not optimal because that corresponds to still correspond to a big function value, right? Where should I pick? Now I'm gonna change the color. Should I pick? No, I give a smallest one, a smaller one. I pick the purple one. Should I pick the smallest, this one? Which one should I pick? Yeah, can everyone agree that I should pick what? I should pick the smallest contour as I can, as long as that contour touch, right? Intersects with the constraint set, which is a straight line in this case. So my optimum point is here. My optimum point is here. This is how I sketch the solution graphically because the problem is enough and allows me to do so. If you don't want to go to that way, graphical way, how can you solve it? Two variables, one equality constraint. I can tell you right now that it's an equality constraint, right? Why don't you write x2 as a function of x1, put it back, it's going to be a function of x1 only, and use the technique you learned from calculus. You're going to get the same thing. Okay, we're going to end the lecture now. Can you do the rest of the exercise as a homework? Use the technique we learned. The important question is that in the remaining problem, try to clarify. I give you the answer already, right? I give you answer already. The P star optimal value is this, optimal point is that. The thing is that in the homework exercise, can you elaborate that? How can you like end up with this conclusion? Especially the problem 10. Oh, the optimal points are not unique. Why? Okay, we end the lecture here. Sadly, not enough time. Okay. มา โอเค